Log on, tune in, find out. Another good idea from Cambridge.
Thanks as the organizer for providing me the opportunity to present my work on inversion of walkaway.
Can you take the microphone?
Big logo.
Yes. Is it better? Yes. Thank you. Okay. So, of course, you know that our aim is to obtain a quantitative image of the subsurface, and we are always in quest of higher resolution, both for reservoir exploration, but also nowadays for the characterization and the monitoring of CO2 storage sites, where we want to be able to detect potential CO2 leakage at an early stage. So data acquisition for seismic prospecting mainly concern acquisition of surface phase data, and you have seen a lot of very nice examples. But well data are also very interested when we want to some detailed studies of the reservoir. So if the quality of well data is often better than the quality of surface data, the image that we can have on the surface of the subsoil is unfortunately of very limited extension. So to clarify what I mean by well data, I will speak of vertical seismic profile data. So acquisition of VSP data means some receivers covering some depth range within a well, and a source that is located at the vicinity of the top of the borehole. So classically, we display VSP data with the receiver depth horizontally and the travel time vertically. So here you have an example of VSP data that has been computing by solving the acoustic wave equation in a model that presents a high amount of heterogeneity. So what you see is the first arrival, which is a downgoing arrival, and you also see many other downgoing arrivals, and these waves have undergone some reflections. You also see upgoing waves that have been reflected in the receiver zone or below the receiver zones. So the presence of these downgoing and upgoing waves reflects the heterogeneity of the medium. And what you see here, in fact, is the interferences between all the scattered waves. So, of course, we can use a classical method used for imaging of surface data to image this data, but like in migration. But as it has already been said, migration assumes a single wave propagation that illuminates the target. And this will not be adequate for such data where we have a lot of scattered waves. So this is why geophysicists generally prefer to account for the whole scattering wave field at the expense of a tremendous simplification of the geometrical aspect of wave propagation. So the approach for inverting such data has been proposed in the 80s by Patrick Lailly and Daniel Massé. And the objective is to reconstruct, it has been developed in a 1D framework. So the objective is to reconstruct an impedance profile from VSP data. And in 1D, you can measure the depth in terms of travel time, and then we can get rid of the velocity distribution. So this approach relies on a solid mathematical basis that leads to a quantitative estimation of the acoustic impedance model. But the strength of this approach is that it does not require any a priori estimation of the seismic excitation, because simultaneously with the impedance distribution, we reconstruct also the pressure condition at the top of the reflector, at the top of the reservoir. And this is really a good point, because in media with a high amount of heterogeneity, our inverse problem may be very sensitive in an error of the source excitation, and which is in practice too poorly known. So the drawback of this approach is that it relies on a 1D assumption. This means that it assumes a 1D plane wave propagation in a 1D medium, so that we only image a subsurface model that is average along the lateral direction. So we are today working on a multidimensional extension of the 1D VSP inversion, and to be clear, our objective is not only to get rid of this unrealistic 1D assumption, but also to obtain an image of the subsoil in the vicinity of the well. So, and this with a resolution that should be much better than the one achieved when we use migration, when you invert surface data, because we will account for all the multiple scattering. But to reach this goal, at least in media that present a high degree of heterogeneity, we will need to retrieve also the pressure conditions so as to get rid of the a priori estimation of the seismic excitation. So we consider 2D or 3D mediums so that it will not be possible to get rid anymore of the velocity distribution. We will assume to have a known velocity field. We will restrict our study to acoustic wave propagation, and we will see in a few slides that we will be also conducted to restrict our model to models presenting some gentle lateral variations. So our extension of a 1D VSP inversion relies on the inversion of walkaway data. So by walkaway data, I still mean receivers covering some depth range within a well, but now the source will be moved shot after shot at different offsets from the top of the borehole. So doing so, we will enlarge the part of the subsurface that is imaged, and so that is illuminated, and thus can be imaged. So as in 1D inversion, we'll get rid of the overburden, the part of the surface that is above the first receiver, by reconstructing also the pressure condition at the top of the receiver. So our target will be the subsoil from the first receiver, and the depth of the target will depend on the recording duration and of course on the velocity propagation. So again, the problem I am considering here is a reconstruction of an impedance distribution. It is not the problem that has been presented this morning by René Edouard and Hervé, who wanted to reconstruct the velocity field. So here we will assume the velocity field to be known. And the main difference with the inversion of surface data is that we will get rid of the overburden, the part of the surface that is above the first receiver. So we will image an impedance distribution below the first receiver, and simultaneously with this impedance distribution, we'll reconstruct S pressure conditions at the shallowest receiver. And this is really a good point, because this will allow us to get rid of an a priori estimation of the seismic excitation. So, however, the reconstruction of these pressure conditions, which is essential if we want to take account multiple scattering in case of a medium containing a large degree of heterogeneity, is the main difficulty of our approach. Indeed, compared with the 1D problem, we are faced with a high increase of unknowns. So we want to retrieve not only the impedance distribution, but also the pressure conditions associated with each source. And obviously, we cannot retrieve these pressure conditions. So to overcome this difficulty, we have to introduce some a priori information. So we currently, in geophysics, introduce a priori information on the impedance distribution. So that's what we do. We restrict our study to model presenting some gentle lateral variations so that we can add a regularization term in our objective function, but this is not sufficient. We also need to introduce some a priori information on the pressure conditions. So here you have an example of pressure conditions that has been computed by solving the wave equation. But you know, in practice, we do not have these pressure conditions. And in practice, in fact, we only have information on the pressure condition in the well. So, and you can imagine that it is very difficult to conceive a method to extrapolate this pressure condition when we move away from the well. So, in fact, we actually make use of the radon transform, which is known in the geophysics as a slant stack, and these procedures transform our data that are associated with different source location into quasi-plane waves through an appropriate combination of time shift data. And the time shift will in fact govern the propagation angle of the quasi-plane waves. So after our random transform, we have in end a set of close to plane, a set of data associated to close to plane wave propagation. And this will be our data. And even if we have not exact plane wave propagation, our pressure condition now presents some regularities that we will be able to exploit. So we will regularize our pressure condition along some directions that will be given by the parameters we have used in our random transform. So I'd like to point out at this stage that even if we had considered a one-day medium, a perfectly one-day medium, our regularization term will not have been exact because in fact we use a Dirichlet condition, and in our data we have some waves that are propagating downward with a certain angle, but we also have waves that are propagating upward with the opposite angle. So this regularization term will never be exact. So doing so, we have replaced our ill-posed inverse problem, here in blue, by a regularized version that will be hopefully well posed. So actually we do not have any mathematical proof of the efficiency of these resolutions, but anyway adding these terms make our problem closer to the reconstruction of a one-day medium, and for the reconstruction of a one-day medium we have some mathematical results that shows that we have a unique solutions up to a multiplicative function, because we cannot retrieve, there is an indetermination between the impedance and the pressure condition up to a multiplicative constant. So we have a uniqueness result, and you have also a stability result, at least for noise-free data. So we have no mathematical proof, but we are very hopeful. So yes, I have also to say that we have weights here, epsilon 1 and epsilon 2, that stand for the uncertainties we have on this a priori information on the impedance and on the pressure condition, assuming a unitary uncertainty on the seismic information. So unfortunately, these uncertainties are very difficult to estimate beforehand. So in practice, we'll use a trial and error approach to get at the end a well balance between the three terms at the optimum. So we have developed a code in 2D. We are working on the 3D version. So in 2D, I will present you an example where we have 400,000 unknowns. In 3D, it will be about 1 million unknowns. our objective function is ill-conditioned, so this calls for adapted numerical solutions. So the solution of the forward problem is based on the solution of the acoustic wave equation. Our quest for high resolution leads us to deal with a finely sampled impedance distribution, so that we use a second-order finite element scheme. However, of course, our computational domain is bounded, so that we want to avoid factitious reflection on the boundaries of the computational domain, and to do that we use perfectly matched layers of Béranger, which consist in surrounding our domain with layers in which incident waves decay. The minimization of our non-quadratic objective function calls for an adaptive optimization solver. We actually use an extension of the quasi-Newton technique that needs the evaluation of the objective function and of the gradient that will be computed by the adjoint state technique that René-Edouard Plessis presented you this morning, since we can compute the adjoint state, the gradient, at the cost of the evaluation of the cost function. And of course, on problem of such complexity, cluster-based supercomputer is essential, and we parallelize our problem through a domain decomposition. So just a word on the optimization technique. So you can imagine that solving a non-quadratic ill-conditioned objective function for typically 1 million of unknown is not a simple job. So classically, quasi-Newton techniques are used to solve optimization problems of huge size. However, our attempt to straightforwardly minimize this objective function leads to failure, because in fact we have two unknowns, the impedance and the pressure conditions, who are of very different kinds and who act very differently on the objective function. The pressure condition, the objective function depends quadratically of the pressure condition and strongly nonlinearly on the impedance distribution. So we decide to decouple our optimization problem between the impedance and the pressure condition. And the process is the following. We minimize the objective function with respect to the impedance using a quasi-Newton method. At each step, this requires the evaluation of the objective function and of the gradient. And to obtain this value, we need the value of the pressure conditions, and these are computed by a conjugate gradient algorithm, since the objective function depends quadratically in the pressure conditions. So it's time now to show you the performance of our method. So I will illustrate this performance on a synthetic model. So our model is 720 meters wide, and 3,400 kilometers deep. So you see that we have chosen models that present gentle lateral variations, but however we have strong variations, strong heterogeneity vertically. So in this model we have placed 100 receivers every 8 meters in a well from 1 kilometer to 1.8 kilometer, and we have sources every 24 meters at the surface. And our seismic excitation is a recurve centered on 25 Hertz. So our objective is to compute from the data that will be recorded at the receivers. So this data, I forgot to say that, are the particle velocity, the particle displacement velocity. So we want to compute from this data the acoustic impedance below 1 kilometer, the velocity field being given. And I will consider two zones: the upper target zone, which is the receiver zone, and below the well, the lower target zone. So we first, as I told you, use a random transform to transform our data to data corresponding to a pseudo-plane wave excitations with propagation angles varying between -6 and 6 degree. And then we tune our regularization weights so as to compute an impedance distribution, and here 13 pressure conditions that of course match the seismic residuals. And here you have an example, the data, the computed data, and the residuals. And an impedance distribution that also match via Fourier information. So you see that our model is very regular, thank you, laterally, and even if we allow some lateral variations. And if you compare the estimated impedance with the exact one, we see the reliability of our quantitative information. However, you may know that to have obtained this image, I have cheated, in fact, because the low frequency are not contained in our seismic data. So, in fact, I have introduced the low frequency as a Fourier information, but without this information on low frequency, I will have retrieved this model, which is a quite good estimation. So, to analyze the resolution, I have here displayed the vertical profiles at the well, 100 meters from the well and 300 meters from the well. So in pink you have the exact impedance profile, and in blue the estimated one. So what you see in the upper target zone, in the zone that is covered by the receiver, you see that the impedance distribution is retrieved with a very high accuracy. Of course, you see a small degradation when you move away from the well. In this zone, in fact, the resolution is governed by the spacing between the receiver. You also see a small degradation when we move deeper. Of course, the low frequency is not retrieved, but you still see a very good resolution. And here the resolution is governed by the multiple scattering. So that, of course, if I had considered a model with less severe heterogeneity, I will of course have an improvement in resolution that would have been less significant. So just rapidly to try to analyze to quantify this improvement in resolution, I have displayed here the spectrum of the seismic profiles, but below the first receiver, since above it is the resolution is governed by the spacing between receivers. So here you have the frequency content at the well and 200 meters from the well for the exact model, the estimated one, and the results that have been obtained by migration. Of course, you see that we cannot retrieve, it's not very clear, but we cannot retrieve the low frequency below 10 Hertz, but what is very interesting is the bandwidth that we retrieve, which is in fact a quantification of the resolution. Rapidly, I have said that we need an estimation of the velocity distribution, which is a very strong constraint. So, in fact, actually, when we have well data, we can analyze the travel times at the well, and we can obtain a good estimation, a very accurate estimation of the velocity in the well. But of course, we cannot obtain this estimation some hundred meters away from the well and below the well. So to tackle the problem of the sensitivity in the velocity distribution, I have run the inversion with an erroneous model that consists in it is a 1D model. The velocity is exact at the well, but you know it is 1D, and below the well it is constant. And I can obtain a good match of the seismic residual, not as good as, of course, as with the exact velocity model, but quite good. And here you see the estimated impedance, which is quite a good result. So again, to see more in detail, I have here displayed the vertical profiles. So again, you see a good reconstruction of the impedance with some degradation when we move away from the well, and some degradation when we go deeper. You in particular see a depth shift, which is in fact due to the error in the time to depth conversion, because we use a strongly erroneous velocity distribution. So to conclude, we are working on an extension of VSP inversion, so as to obtain a reconstruction of the impedance distribution with a vertical resolution of a few meters and a lateral extension of a few hundred meters around the wall. Of course, this resolution depends on the presence of multiple scattering, so the resolution will be much better if we consider a medium with high heterogeneity. This needs appropriate regularization techniques, and in particular you have seen that we only deal with the models that present gentle lateral variations. This model also needs a reconstruction of the pressure conditions, and this is really a good point because it allows us to get rid of the estimation of the seismic excitation, and it also requires adapted numerical solvers. So the context is it requires a velocity field. We are limited to acoustic waves, and I have also mentioned the gentle variation. So just to end, I will say that some works need to be done. So the 3D extension is still in progress. We also want to use homogeneous transparent boundary conditions that will be better suited to our problems than the directly boundary conditions that we are actually using. And we also want to see how we can update the velocity model during the inversion. And a main problem, which is a geophysical problem, is to try to design seismic acquisitions to optimize the reliability of the quantitative estimation and the vertical resolution when we have identified the target. Where do we have to put our receivers, our source, to have the best resolution? Thank you very much. Oh, yeah.
Very much, Florence. While we are setting up the next talk, Ivan, questions? Yes, Hervé.
How strong are multiples compared to primaries in this case? And does it play a role?
Yes, it's essential. So I have chosen a model with a very tensioned model, so with very strong multiples, and that's why we have this improvement in resolution. Of course, if I have a small model, this method will not be better than. This is really the key point. But to reach this goal, we need to recover the pressure condition, and this is a difficulty. But I think that it's a powerful method if we can retrieve the pressure conditions.
And in fact, the difference in 2D compared to 1D, that in 1D you have scattered multiples, but in 2D you may have multiples coming from scattered points, yes, or from reflectors.
Yes. Yes, but this is why also in 2D we can have this resolution quite far away, but not too far away from the well, because we then have a large part which is eliminated and with different illumination angles.
Yes.
How do you choose two regularization parameters?
The weights?
Yes.
The weights. So. In principle, they are related to the uncertainties we have on the information, but we do not have access to the uncertainty. So today, what we are doing is that we are tuning the weights so that at the end we have a good balance. We look at our results, and we want a good residuals on seismic data and the good residuals on a priori information. So typically, if I choose epsilon 1 and epsilon 2 too slow, I will have good seismic residuals, but then I will have some difficulties to regularize my pressure conditions, for example, and then my algorithm may not converge. So it is really a trial and error approach. On the contrary, if I choose epsilon 1 and epsilon 2 high, then I will have close to a 1D problem, but I will not explain my seismic data. So this is a trial and error approach.
speaker again.